And now let us look at the third. So far we have looked at stress life approach, and then now we need to look at LEFM approach for fatigue crack growth. So far, how the fatigue crack grows, and can we predict the crack growth, how the crack growth is happening in the material, right. So now let us look at this figure. The first one actually shows the crack length as a function of number of cycles, and the second one shows you the stress as a function of number of cycles. Okay. So here let us say AD is the minimum detectable crack length. D stands for detectable. So in any material, if by doing an inspection, depending upon the resolution of the equipment that we are using, we will be able to find out a crack length of say for instance 1 mm is the resolution. You cannot detect a crack whose length is less than 1 mm. Okay. So now let us say that the AD is the minimum detectable crack length in the material, and then AC is the critical length reached from AD, where brittle fracture occurs after NIF cycles. F is failure cycles of loading. So suppose if you are loading the material, if this is your initial, so every crack that we have, so you do not have cracks, you do not know this is the minimum crack length, you do not have any crack which is actually larger than AD in the material, right. Let us say you have a crack whose initial length is AD, then you are loading, you are applying fatigue loading on the material. After NIF cycles, the crack length reaches a critical value of AC, that is when the material breaks as if it is a brittle fracture, right. As we have seen in the case of a fracture mechanics module, when the crack length reaches critical crack length, that is when the material breaks as if it is a brittle material. The same thing we are doing here. And so here we are having A versus N, and the slope of this line is dA by dN, right. That is your tells you crack growth rate. A is the crack length here, and N is the number of cycles. Now let us say for this particular material whose initial crack dimension, maximum size of the crack to begin with is AD, and if this particular component is designed for service life of n hat cycles, that means you are designing this guy for to last for n hat cycles which are less than NIF cycles, then you can define, as we have already discussed, the factor of safety in life can be written as Xn equal to number of cycles for failure divided by service life, right. This is number of cycles to failure divided by service life for which the component is designed. This is something called factor of safety in life that we have already looked at when we are talking about crack that is actually growing in size. Now as this crack grows, right. So initially at 0 cycles you have the initial crack length to be AD, the minimum detectable crack length. At that time let us assume that the strength of the material is this guy, SC is this much. Okay. Now you can say that the critical strength of the material is equal to Kc by beta root pi a, where beta is your geometry factor. You remember we have written K equal to sigma root pi a, where sigma is your stress, right. So when this becomes your critical strength of the material, then we call it as sigma c. So now this sigma is represented by S, that is the only thing. So Sc becomes K becomes fracture toughness then. When this becomes critical, that means this should be fracture toughness root pi a. Okay. Now as you increase the crack length of the crack, as the crack grows, we know that the strength of the material Sc decreases, as you can see from here. As the length of the crack is increasing, the Sc reduces because the length of the crack is in the denominator. And then so this graph here actually shows the reduction in strength as the number of cycles are increasing, because as the number of cycles are increasing, your crack length is increasing. So, now if n hat cycles is the prescribed life for this component, then the safety factor in stress due to applied cyclic load x c is given by S c divided by S max. So, S max is the stress at which it actually fails, and then S c is your the residual strength in the material, right. All right. So, sometimes however, the safety factors suggested by x n and x c are not sufficient due to a combination of unexpected AD, because you are saying that the AD can actually also suddenly change because of the cyclic loading nature and sudden unexpected loads that may be there, or unexpected crack detection mechanisms that are available, and hence AD that we have measured might as well be having some error associated with that. And hence alone x n and x c alone, sometimes the suggested values may not be sufficient for the design. Sometimes failure may occur even for x n less than 1, right, for that reason. Hence, it is extremely important to ensure that your detectable crack size is well within the safe limits, and hence a periodic inspections are needed to repair any cracks that are larger than AD. So, you are saying that my initial crack length detectable crack size should not be greater than AD. So, you need to ensure that they are indeed not greater than AD. Several machine components actually they may start with an initial crack length AD, but during the service they may increase in size, as we have seen. As the number of cycles increase, the size of the crack increases, but it is possible that this size of the crack might not increase the way that we are expecting. It might increase much faster, much more at a much steeper rate, and so on, right. So, that means we need to do periodic inspections and ensure that the initial crack length should be the crack length at the time of putting the system into commission should be well within AD. So, if the periodic inspections are done for every NP cycles, let us assume, then the length of the worst crack increase can be shown here. So, this is your failure happens at NIF cycles, let us say. Then your initial crack, which is AD, increases up to here. That means the crack length has increased from AD to some other value greater than AD. Then since you have done an inspection at NP cycles, after NP cycles, then you will see that my crack length is larger than my detectable crack size or expected allowed crack size. Then what you can do is you can actually do some repair to the crack and then reduce the crack size to AD again, and then you do the further continue the loading, and then again inspect after NP cycles from the first inspection, and then if there is any increase in crack which is expected to be there, and then you do the repair and so on. That means the safety factor in life at this point of time is NIF divided by NP, because we have done the inspection at NP cycles. So, after each inspection what happens? You are repairing the crack, and as a result, so up to during this process, as the crack length is increasing, the residual the strength of the material is decreasing, but at the end of NP cycles you are actually doing the repair to the crack. As a result, the strength increases again, and then it continues again, and so on. And so, the safety factor on stress during this entire process is lowest just before the inspection. Once the inspection is done, the safety factor on stress is increased, because you have done the repair to the crack. The crack length has actually reduced now from AD plus some value, AD plus delta to AD. All right. So, here that means during this process we can actually monitor how the crack is growing. So, the rate of crack growth as a function of number of cycles denoted by dA by dN plotted against the stress intensity factor range delta k. That means k max minus k min. What is k max? That is sigma max root pi a minus sigma min root pi a, or S max root pi a minus S min root pi a, right. That is equal to sigma max. So, that means delta sigma root pi a, that is your delta k, that is what we are plotting. So, this plot, when you plot on a log scale, shows a sigmoidal behavior as shown here. Okay. So, the region 1 here is what we call crack initiation stage, and this is what is called crack propagation stage, and then this is unstable crack group. Region 2 is crack propagation stage and region 3 is unstable fracture. And for us, region 2 is very important because here the crack is propagating in a stable manner. Well, that means even if the crack propagates, it is not going to cause any catastrophic events in the component's service life. So, if you know when does stage 2 end, then you can actually say that how many more cycles can I use, or for how many more cycles can I use the component. So, this is a very important information that one would be able to get by looking at the relation between dA by dN, crack growth rate, and the fatigue and the stress intensity factor range. So, it is observed that this dA by dN versus delta k, when plotted on a log scale, the region 2 shows a straight line behavior, and this is something that was observed by Paul Paris, and then he gave a relation to dA over dN, the crack growth rate, to stress intensity factor range in the region 2, that we will see the formula how it looks like. So, here let us look at carefully the 3 regions. So, the initial steep region at low delta k values. So, it gives you a threshold delta k th. So, in this region there is no crack growth, right, and below delta k th there is no problem for the material, the cracks do not grow at all, right. And now in the region 2, which is a linear regime, which is actually a stable crack growth regime, and final steep region is an actually unstable crack growth regime, right. So, this is below delta kth no crack, this is stable fatigue crack growth and unstable crack growth. So, the part of the curve in region 2 is a straight line on log coordinates. So, Paul Paris defined the relationship in region 2 as dA by dN equal to C delta k power m, where C and m are your material constants. So, once you know the material constants and you know what is the delta k, and then integrate this equation in order to get fatigue crack growth life. And usually for several materials, for steels m equal to 3, and for aluminum alloys it ranges from 3 to 4 in general, but other materials, if we want to find out what is the value of m, one can find out from the design data handbooks. And region 1, so we said region 2 is more interesting because that gives you an information about fatigue crack growth in a stable manner. So, it allows us to calculate the remaining life of the component by knowing the initial crack length. So, region 1, however, region 1 is also interesting as it shows the threshold limit kth, below which there is no crack propagation at all, absolutely no crack propagation. So, usually delta kth occurs at crack propagation rates of the order 0.25 nanometer per cycle, extremely low crack propagation rates, and hence we can consider them there is absolutely no crack growth at all. However, region 3 is something called accelerated crack growth regime, in which the k max of the applied load approaches the Kc, that means fracture toughness of the material. When the Kmax becomes equal to Kc, that is when the material breaks suddenly as if it is a brittle fracture, and hence that regime is characterized as unstable crack growth regime. Okay. And now, what is the effect of mean stress on this crack growth or crack growth rate? So, increasing the stress ratio, that is R, that is equal to sigma min by sigma max, in other words K min by K max, has a tendency to increase the crack growth rate in all the regions. However, the effect of increasing R is less in region 2 than region 1 and region 3. So, how do we incorporate the effect of stress ratio on Paris law? So, one such ways to incorporate the value of R on dA by dN is this. So, dA by dN is equal to C delta K whole power P divided by 1 minus R times Kc is the fracture toughness minus delta K. So, here the effect of stress ratio has come in. So, that means as you increase the stress ratio, what happens? As you increase the value of stress ratio, this quantity reduces, right. As a result, dA by dN increases, as we have already seen. Increasing the stress ratio has a tendency to increase crack growth rate. All right. So, how do we go about using this in the real life design? So, you actually do a laboratory test on a specimen of the kind of loading that you would expect in the real life scenario on a laboratory specimen, and then do this for different delta P's. Delta P is P max minus P min, as we have seen here. P is your load or load applied, and then you calculate the dA by dN as a function of different delta P's, and then from this you plot this guy. So, dA by dN divided by dN as a function of delta K. Delta K is calculated from delta P. So, for delta P1, delta P2, delta P3 you will get different values. So, as many delta P's you can do. So, then you will get several values, and all of them you will fit a straight line on a log scale, and then from there you can calculate your C and M for that particular material and the geometric scenarios, and use that information now for real life applications, wherein you know what is your stress. So, your delta K equal to F times F is your like your beta, the geometric factor, delta S is the stress range, and A is your crack length, and then use whatever formula that you have C and M that you have obtained from the laboratory tests, and then use that in the real life application, and then you will be able to calculate from there. You will be able to calculate what is my residual crack life, or what is the more how much more crack length increase can I accommodate based on the loading scenario that is there in the material. So, this is a simple one example problem wherein you have a mild steel plate which is subjected to constant amplitude, the amplitude is not changing, uniaxial fatigue load to produce stresses varying from sigma max equal to 180 MPa, sigma min equal to minus 40 MPa. Please pay attention here, minus 40 MPa. So, the negative 40. So, the static properties of the steel are sigma naught, that is your yield strength, this is your yield strength, SU is the ultimate strength, and E is elastic modulus 207 GPa, Kc is your fracture toughness 100 MPa root meter, and if the plate contains an initial through thickness edge crack of 0.5 mm. So, initial crack length is 0.5 mm, how many fatigue cycles will be required to break the plate. So, you know this is the material and you know the loading scenario like that, and if you have an initial crack edge crack length of 0.5 mm, the question now is how many fatigue cycles can be will be required to break the plate. That means, how many fatigue cycles can this component be used for before it actually breaks, in other words, and you assume an infinite width of the plate and for which beta equal to 1.12. So, the reason the infinite width has been given because the geometry factor comes into play, and the geometry factor for k is equal to sigma root beta times sigma root pi a, the beta value is given 1.12, and c equal to 6.9 into 10 power minus 12. Okay. So, the solution, so we know that this is mild steel. So, for steel m is given as 3 in the formula dA by dN is equal to C delta k whole power m. This m is given as 3 and C is now given here in consistent units. Then dA by dN we need to, so dA by dN is equal to C delta k whole power m. So, C is plugged in, m is plugged in, and delta k. How do we go about calculating delta k? So, this is your initial crack length, A equal to 0.5 mm. So, I am writing it in meters divided by 1000, and the final crack length is equal to, so final crack length means crack length at which the fracture happens. Fracture happens when the fracture toughness, the stress intensity factor reaches the fracture toughness. So, the final crack length is equal to Kc by sigma max beta. So, where we are talking about sigma max whole square, right. This is coming from k equal to beta times sigma root pi a. When this is becomes Kc, then this should become sigma max. So, using that for that equation, we have figured out that the final crack length should be 0.078 mm. That means, the material breaks when the crack length reaches from 0.5 meter mm to 0.078 meters or 0.0005 meters to 0.078 meters, right, or 78 mm in other words, 0.5 mm to 78 mm. All right. So, now you note that the stress cycling is happening between 180 MPa to minus 40 MPa. So, this is 180 and minus 40 somewhere here. So, right. So, there is some mean stress in the system. So, you actually have R is coming into picture. However, we will neglect that part in this scenario, and delta k is k max minus k min. However, note that k min is negative 40 MPa, minus 40 MPa, but when you have compressive stress, the crack growth will not happen, and hence whenever you have a compressive stress, you should not take that into account, and hence you can take k min equal to 0. It actually compressive stresses will be beneficial, but here we are not taking into account of the benefit whatsoever into account. We are simply saying that since the k min is actually coming out to be negative, so we will not take that into account, and then we will say k min equal to 0. So, sigma min equal to 0. So, then you write dA by dN is equal to C delta k power m. So, delta k becomes simply k max. So, k max is given by beta sigma max root pi a whole power m, that is your dA by dN. So, now you integrate this equation, and when you are integrating, dN should be integrated from 0 to nf, whereas initial crack length is ai, final crack length is af. We know what is af, we know what is ai, and you can integrate this expression. C is known, beta is known, m is known, sigma max is known, and then dA by root pi a. So, that becomes something like that, and then once you integrate this, you can find the definite integral and all the values are known, and then plug that in, and then you will be able to calculate nf equal to 261,000 cycles. That means, when you have the initial crack length to be 0.5 mm for this given system, you can run the equipment for 261,000 cycles, provided in between you are not doing any repairing. If at all you are doing periodic inspection, then you are actually repairing the system. That means, the crack length is brought back to 0.5 mm that is say initial AD, that is detectable crack size, then your life might be increased further. Here we are not assuming any intermediate inspection and repair of the specimen or the component. Okay. So, this is how one would be able to calculate the remaining life of a component by knowing what is the initial crack size and other properties of the material together with the loading type of loading that can be applied to the system. Okay. So, with that we have understood how do we go about calculating the remaining life from the fatigue crack growth point of view. That means, you have an initial crack and you are letting the crack to grow, and what is the limit up to which you can actually continue to use the system, right. All right. So, with that we sort of close this module on failure theories on fatigue failure theories. So, these are the textbooks that I have used extensively during this module. Robert L. Norton's Machine Design, an Integrated Approach, and George Dieter's Mechanical Metallurgy to discuss some of the microstructural details of the fatigue crack growth, and Mechanical Behavior of Materials by Mayers and Chawla is another interesting textbook, and Norman E. Dowling's Mechanical Behavior of Materials. Okay. So, with that we will close this module on fatigue failure of materials, and then we will meet with the new module in the next class. Thank you.